Alrighty, so welcome back to class. Sorry I was out last week. Family stuff going on, but it's all taken care of now. So let's see here. Okay, I want to talk about quizzes. So I posted a new quiz on OpenMP. 10 questions, should be fairly simple, straightforward. And then I wanted to just go over the last two quizzes. Let's go ahead and hit preview, I guess. I think everybody got full score on this one. But I'll just go through these real quick. The path environment variable is, even Windows has a path. Okay, they all need this because they need to know where to find programs. When you say a program, it needs to know where to look to find it. And so that's what the correct answer is: a list of directories. In Linux, what symbol is used to represent the root directory? In Windows, we have that one. That one is the bash terminal symbol. That is a shortcut for your home directory, and that is the root directory. The rm command is dangerous because it unleashes hordes of raptors. No, because there is no undo button. It deletes stuff, and you can't undo it. I did this one to force you to Google something useful, and that is the -I flag, which stands for interactive. It will ask permission before it does anything. In order to copy a directory, you want to use the -R flag. I did try and put the -F in there to make it for force, but I don't think there is one. Submitting projects for this class, everyone's doing a pretty good job with that. And then version control systems are used to track changes to your code. I wish it could be your personal Jarvis. That would be nice, but you can't. So this one was a little bit more tricky. And I did have a mistake, but the first person who took the quiz caught it. So, which of these memory devices can load to the CPU the fastest? That is going to be your cache. The cache is located directly on the CPU. We want, if possible, to keep everything in the cache. Cache lines, why are they used in computer architecture? It's because they increase the cache hit ratio, generally speaking. What they do is they take out an entire chunk of memory at a time, assuming that you're going to want the next object in memory. And so that way it's all in the cache and you can keep going. Otherwise, you'd be pulling one object at a time, and you'd always be generating a cache miss, which takes more time. And I guess technically they do increase pipeline efficiencies because then there's no bubbles, but that wasn't exactly what I was going for. So sorry about that. Typically the best way to speed up a code is to use a better algorithm. Okay. Obviously we're doing pretty simple stuff here. For instance, the computing pi with the random dots is not a very good way of computing pi. Okay, so if you want to speed it up, don't make it go in parallel. Find a better algorithm. It's not very accurate either. Pre-computing lookup tables is a trick that can work sometimes. Writing your code in assembly, that's only if you're a masochist or a computer engineer, which I guess those two are the same thing. Using super-fast linear algebra libraries, that is just a nice thing to know. It's not your algorithm. So you get the correct algorithm. If the algorithm needs math, then you go find the right linear algebra library. SSE instructions are what type of instructions? They are single instruction, multiple data instructions. They do one thing on multiple pieces of data at the same time. Which of these optimizations can compilers generally perform? That would be inlining. They can't change your algorithm because they only do exactly what you tell them to. Aliasing is not an optimization. It's more of an anti-optimization. And loop blocking is generally too complicated for a compiler to do correctly. In C++, large classes should always be passed by reference. If you have football players in your computer, I'm confused. But reference just passes a memory address. In a similar fashion, you could use a pointer, but reference is generally preferred over pointers. So if you don't know the difference between those two, just go with reference on all accounts. Overloading operators can have a significant impact on performance because it takes time to construct, copy, move, and destruct all of the temporaries. So that's something to know about. And all of that does interfere with optimizations, but that's the primary reason. When writing fast code, it's generally better to use the structure of arrays pattern. Everyone got that, so I was happy with that. Allocating memory is a performance bottleneck because it takes time to allocate and delete memory. I found out the other day that the actual code that does the allocation is 5,000 lines long. So that takes time. Profiling a code is used to understand where to optimize the code. That one should have been fairly simple. The rest of the answers didn't make much sense. So there's that. And then, so anyway, this quiz is due this Saturday. We have the project due. Project 3 is due on Wednesday, and I have posted Project 4. I talked about that last week in the lectures that I posted online. And I've put up a project description.
So that's due the 22nd?
Yeah, so that's due next Wednesday, in a week. I figured since we got through the hard part with Jacobi, making it Gauss-Seidel shouldn't be too bad. So here's the project description. I have a short little thing on the red-black scheme, which I also talked about in my lecture from last week. Drew a little picture for you so you can see. The strong scaling and weak scaling is all the same. I just copied that straight from the Jacobi. And then on what to turn in, I want you to tell me, does the red-black scheme seem to scale better or worse? And then why do you think this is? Couldn't give me any reason you can think of. And so that should be pretty good. And then I had a question on what it means to run the scaling studies. I am okay with just doing n equals 100 strong scaling. Yeah. Because I don't want to sit here forever. So whatever you do is fine, but minimum just that. I just want to make sure your code actually works. So that's project 4. That will be due next Wednesday. So as for, let's see, is that everything I wanted to go over? I think so. So in lecture notes today, I've posted our first MPI program. Okay, and I'm going to show you a demonstration of this today. And then I've got my lecture slides for today up as well. Okie dokies. We got another one. Okay, so today we're going to be talking about distributed computing and MPI. So, distributed computing is the opposite of shared computing. Instead of having one computer with multiple processors, we're going to have multiple computers which are connected by some sort of network. We call it distributed because the memory is actually physically distributed across the computers. And because of that, it's not possible for computer A to access the memory on computer B. And so in order for the computers to work together, we have to pass messages to each other. And that network could be the internet, although that's generally a bad idea. It could be an Ethernet network, like your Xboxes that you plug together. Or generally what you'll see on HPC clusters is something they call InfiniBand. I actually have no idea what that is, but that's what they call it, and that's what they use. So, and there's a bunch more out there. For our purposes, we don't really care. Just the faster the network, the better. The textbook actually goes a lot into networks. And it can be really important if you want to get scaling to go up really well. If you want your scaling to go up to 100,000 processors, you need to know that stuff. You're not going to be able to get that good unless you know exactly what hardware you're running on and all of its quirks and intricacies and all that other fun stuff. But we're not going to worry about that because I doubt we're ever going to be getting that big. And if we are going to be getting that big, we're probably going to be using someone else's libraries or programs. So, now, all modern hardware is a hybrid model. Okay, we have a lot of nodes, and each node has multiple shared memory cores. Each node is then connected to each other through the network. So a purely distributed model, a purely distributed setup would be 4 processors, 4 chunks of memory, and the network connecting them all. Okay, so that is how we are going to envision it. All right. In real life, however, what we have is something more along these lines. Okay, so these 4 processors technically all see the same thing here and here. Okay, so they could work together. In fact, you can do that. You can actually have an MPI program that runs using OpenMP. But that's really advanced, and we're not going to do that. And for most purposes, it's really not all that necessary. Because it is possible to write MPI programs that run faster than OpenMP programs on shared memory. Because of the flexibility that MPI gives you.
So if that's the case, then what's the point of OpenMP? It's just easier?
It's just easier. Yeah. OpenMP does a lot more stuff for you than MPI does. So, ever since distributed computing was invented, people have argued about how to program for these systems. And there's been, starting back in the 80s when these things first came about, I mean, Cray had their own thing, and Intel had their own thing, and IBM had their own thing. And anyway, eventually they all kind of got together and they said, this is stupid. We need to come up with a unified system. And message passing interface rose from the ashes of that. So what this is a basically the idea is each computer is going to send messages to the other computers, and the other computers can catch them or receive them and do stuff with them, and then send information back to the other computers. So MPI is a standard, just like OpenMP is a standard or C++ is a standard. Basically, they say a bunch of people got together and said, this is what it has to look like, this is what it has to do, and then other people actually implement that standard. So they actually write the code that does what the standard says it should do. And so at CHPC, they have 4 different MPI libraries available for you to use. They have MVA PICH2, they have OpenMPI, which is the default Linux MPI. They have MPICH, also known as MPICH2. And then there's the Intel versions of MPI. And guess which one tends to be the fastest? Intel. Now CHPC actually has a lot of really good documentation. What? Okay, that's great. At this website here. Okay, and so they basically explain how to use MPI on their hardware, explain the differences between these 4. And I skimmed through this today. The most important thing, they compare and contrast all of these things, but they do say that the OpenMPI, which is free, I should say the first 3 here are free. Intel's is not free, which is probably why it runs the best. But they say that OpenMPI, while being the slowest, is actually the most user-friendly at the same time. So
as far as like syntax, but I know we don't probably care but for this class, but as far as, is the syntax similar between them, or is it way different?
The syntax is similar. So the standard specifies that you must have a wrapper compiler, which I'll show you, and you must have like an MPI run. They don't say anything about how they're supposed to actually work, but it says you have to have those 2 things. And so I'm going to talk about that a little bit. So if you're confused about which one to use on CHPC, I'd go with OpenMPI because it's apparently kind of just point and click, easy to use. So back to the presentation that apparently broke. All right, so there are a couple of tutorials. There's this one, which is actually pretty good, called mpitutorial.com. And there's another far more technical one put out by the Lawrence Livermore National Lab here, but they detail everything. So if you ever want to know anything, you can come here. It's computing.lawrencelivermornationallab.gov tutorial/MPI. And if you just type in MPI tutorial into Google, it's the first thing that pops up, for me at least. So, and then MPI tutorial is the second one. So, let me just give you a demonstration of how we code an MPI program. All right, so this is a simple hello world program. So the very first thing to note, you have to include the MPI header file. Okay, and it doesn't matter what distribution you're using, they all have this header file. So you have to include this so you have access to its functions. And every MPI program, the very first MPI call of any kind must be a call to MPI init. And you send it the argument count and then the actual arguments. What it does with them, I don't know. But it takes them, so you have to send them to it. Okay, and then some basic stuff here. So we have an integer called my rank. We have an integer, the number of processors being used, the length of the processor name, and then the actual name of the processor is going to get stored in this character array. And so we have a call to MPI com size, and I'll explain a little bit more what this is. But we have then this big thing in all caps, MPI com world, and then we send it a pointer or the address to the integer number of processors. And what that's going to do is it's going to store the number of processors contained in MPI com world. And we have a call to MPI com rank, which does the same thing, except I should say each processor that's getting used has a rank assigned to it by the MPI library. And so this gives you access to that. So now you know what your rank is. And then this one probably doesn't get used very often, but I think it's kind of cool. You can get the name of the processor. And then I'm going to output all of this stuff. And then the very last call is to MPI finalize. Once finalize has been called, you cannot call, it is an error to call any MPI function at all. And so in order to compile this, we're going to use the MPI wrapper compiler. This isn't a compiler proper. It doesn't actually do any compiling on its own, but it adds the correct linking flags and include flags around the compiler that you've been using. So in this case, we can actually do this, and you'll see MPI CXX actually has no version on its own. It actually redirects that to the G++ compiler. All right. So we can compile our program. It compiles and it spits out a dot. So we run it. But wait, we wanted to run it with more than one processor, right? So how we do that is we use a separate program. So MPI run is a program that runs your program. Okay. Oh, and it screws up because I did that completely wrong. There we go. That's better. So now we get two. We have a rank 0, a rank 1. There's two processors, both of them running on, of course, my Mint VM machine. So what MPI run does is it sets up your environment, and it says, okay, I need two processors, because that's what I told it with my -n flag here. And then it's actually going to run two completely separate programs of a.out. If it ran longer, you could actually see it in like your task manager. You'd see two programs running. And those two programs don't know anything about each other. The only way they're connected is through the MPI library and through its functions. And so that's something that's really important to note, is there's no parallel region like there is in OpenMP. It's all parallel, because you have program A running over here and program B running over here. And the two CPUs are running through it separately. They don't know anything about each other. Okay, which means we get to do a lot more stuff manually that OpenMP does for us. So that, let's see, back to the presentation. So that's kind of the basic functionality.
What's MPI exec? Same thing as MPI.
Yeah, and I really don't know the difference or if there even is a difference, but I have seen that used.
Okay.
But I've always used MPI run. So if you want to get MPI on Linux, you just use this command. So mpi-default-dev, that gives you the header files and the binary files. mpi-default-ben, that gets you the wrapper compilers, and MPI run.
On the cluster, though, all you have to do is...
On the cluster, you have to load the correct module. And I haven't gone through and made sure I completely understand that yet. I'm going to get to that next time.
Oh, okay.
How we use it on the cluster. So anyway, yeah, I think that's about all I had for everyone. I know it's 20 minutes early, but I was waiting for carpet cleaners yesterday all day. Never showed up. Anyway, yeah, that's all I had for you guys. So any questions?
Not yet.
Okie dokie. Then there you have it. We'll go ahead and stop this thing.